In Unit 11, we really take integration to the next level. In 6.1, we're going to find the area between two curves. Then we're going to find the volume of revolution using the disk and washer method. And finally, we'll look at volume of a solid using a different method called slicing. For 6.2, we're going to look at the volume of a solid of revolution using the disk and washer method. So what that means is we're going to take the volume of a function f of x revolved around the x-axis. So we take this function, that's my f of x, and I'm going to spin it around the x-axis. I'm going to get this solid. In this case, it kind of looks like a rounded off cone. So this whole thing will become, like this whole area will be a solid. And if you notice, if we slice it, we're going to get these disks. So these disks are circles. We need to find the volume of each one of these circles, and then we add all those circles up. So the formula here, so we need to find the volume of this disk. And the volume of the disk is going to be pi r squared, that's the area of the circle, times the height of the disk, which is delta x. So that's where this equation comes from. It's my pi, it's a constant, it just comes on the outside. We're going to go from A to B. Those are my endpoints, from A to B. And then the function is my radius, here, squared, times dx. And here the radius of the disk is going to be f of x. I really encourage you to play around with this some more to see what it looks like, because this is super powerful and really cool that we can find the volume of any shape, not just those platonic solids that we're used to finding from MCAS. All right, let's take a look at example 1 on page 478. It says, find the volume of a solid of revolution generated by revolving y equals the square root of x, the x-axis, and the line x equals 5 about the x-axis. So you can see first thing they do is they draw the picture here. That's the line y equals square root of x. We're going to go from 0 to 5. And we're going to revolve it about the x-axis. So that's what this is showing us. So we are going to get these disks, and each one of these disks will stack up and make this solid. So my area is going to be pi 0 to 5, and then the square root of x squared dx. So let's simplify that. My volume is going to be from 0 to 5, x dx, and we know how to find that. That's going to be 1/2 x squared evaluated from 0 to 5. So the pi will just come for the ride. I guess I could actually move the 1/2 out there to come for the ride also. And then 5 squared minus 0 squared. So that's 25 over 2 pi. And that's the volume of this solid. Let's take a look at 6.2. It's a little bit more complicated, but we're going to do the same process. So it asks us to find the volume of a solid of revolution generated by revolving the region of the graph y equals x cubed, the x-axis, and the line x equals 1 and x equals 2. X equals negative 1. So the first thing, just like we did before, we're going to have two pieces. We have this piece, and then we're going to have this piece. We need to revolve both of them around the x-axis, and you see we get this 3D shape here, where this is one part, and then that is the other part. So let's see what we're going to do for our volume formula. The volume is still pi, because we're using the disk method, so it's always pi on the outside. The first line we're going to start at is negative 1, then we go to positive 2. My radius is x cubed squared times dx. All right, let's simplify that. That's pi, goes from 0 to 2, x to the 6th dx. So the antiderivative, pi will just come for the ride, 1/7 x to the 7th from negative 1 to positive 2. I'm going to pull the pi over 7 out just to make it a little bit cleaner. And I have 2 to the 7th power minus negative 1 to the 7th power. So let's see, 2 to the 7th. I don't know, that's a pretty big number. Is 128. And then that's a negative 1, because it's negative 1 to the 7th, so plus 1. So I get 129 over 7 pi. And that's the volume of that shape, where I have this piece and this piece all together. All right, for this problem, we're going to go around the y-axis. So it's the same basic idea, except for we're going to be doing it, oops, that should be g of y dy. So the same formula, that it's pi r squared times the distance. I'm going to say times the height. But this time, the pi comes on the outside. It's going to be g of y squared and then dy. So here you can just see the little arrows rotated around the y-axis. So we're making these discs that are like perpendicular to the y-axis or parallel to the x. And we're going to go from C to D. So this point on the y-axis. Let's try this in a problem. Use the disk method to find the volume of revolution generated by revolving the region bound by the graph y equals x cubed, the y-axis, the line y equals 1, and the line y equals 8 about the y-axis. So what we're trying to do is find this function here and then revolve it around the y-axis. So the first thing we need to do is solve for it to be x equals instead of y equals. So we'll take the cubed root of both sides, so x is y to the 1/3. Now that's the function that we're going to revolve around the y-axis. They gave us the points 1 and 8, so those are my endpoints. So we're going to go from 1 to 8. Pi, my radius is y to the 1/3, squared dy. So it's pi, the integral from 1 to 8, y to the 2/3 dy. We add 1 to the exponent, we get 5/3, and we multiply by 3/5. Evaluate it from 1 to 8. Again, I can pull out that 3/5 pi. That's just makes my multiplication a little bit easier. And we'll plug in 8 to the 5/3 minus 1 to the 5/3. So 8 to the 5/3 is the cubed root of 8, which is 2. And then 2 to the 5th power, 32. And then 1 to the 5/3 is just 1. So that's 3/5 pi times 31, which I could write as 63 over 5 pi. And that's the volume of this shape, kind of this cut-off cone. So previously in 6.2, we've been talking about creating disks out of volumes when we rotate a function around either the x or the y axis. And this time we're not going to just get one thing, one shape. We're going to actually have two shapes. So there's going to be a hole in the middle. And this hole, you can see it right here. When we rotate, we have the first function, then the second function. I'm going to rotate it around the x-axis, and I get this hole. So I need to account for this hole. So there's like something missing in the middle. And the way we're going to account for that is the same idea of the volume equals pi r squared times the height. But this time my radius, it's going to be the inner radius minus the outer radius minus the inner radius. So that's f of x squared minus g of x squared. So that my whole integral becomes pi, the integral from a to b, those are my endpoints, f of x squared minus g of x squared dx, because x is my variable since I'm rotating it around the x-axis. All right, let's actually put that into some practice here. An example 4 on page 482. Find the volume of a solid of revolution by revolving the region bound by the graphs y equals 2 over x and y equals 3 minus x. So we have this region right here, and we're going to rotate it about the x-axis. We're going to get this little loop. So it's going to look something like this one right here. And we're going to find the volume of each of these disks and then add them together, which is essentially just taking the integral. So let's write out our formula. It's going to be, oh, and they told us the endpoints where they intersect. We should find those endpoints where they intersect, so I'll just go through that. So we do 2 minus x equals 3 minus x. And let's see, we'll multiply through by x, so we get 2 equals 3x minus x squared. So x squared minus 3x plus 2 equals 0. So x minus 1 and x minus 2 equals 0. So my points are x equals 1 and x equals 2. So those are going to be my endpoints on my integral. So my volume is going to be pi times the integral from 1 to 2. And the outermost functions, that top function, that red straight line, which is going to be 3 minus x squared, and then minus the blue line is the curved, it's the bottom function, so minus 2 over x squared dx. And I'm going to do a little bit of simplification here before I take the antiderivative. I think that we can make this look a little bit easier to handle. So the first thing we're going to do is FOIL out 3 minus x squared. So that's 9 minus 6x plus x squared, and then I'm going to distribute that negative sign, that squared to each piece, so that's minus 4 over x squared. And I could even rewrite that minus 4 and then x to the negative 2 dx. And this might be a little bit easier for me to take the antiderivative of. So we have pi 9x minus 6 over 2, or 3x squared, plus 1/3 x cubed, minus, and then let's see, we're going to go add 1, get negative 1, and 4 divided by a negative 1, or plus 4 I could write that as. I'm going to evaluate that from 1 to 2. So we have pi 9 times 2 minus 3 times 2 squared plus 1/3 2 cubed plus 4 over 2, and then minus 9 times 1 minus 3 times 1 squared plus 1/3 of 1 cubed plus 4 over 1. All right, so let's simplify all of that. I'm going to get 1/3 times pi, or I could say pi over 3. So that's the volume of this blue disk being created here, or this blue figure being created here, is 1/3 pi. In example 5, we're going to do the exact same thing. We're going to revolve around the y-axis. So we're going to take this shape inside here and revolve it and get this kind of like a silo looking figure. So the first thing we're going to need to do is find those points of intersection. So let's do that first. So 2x equals x squared. So we're going to get x squared minus 2x equals 0. So x minus 2. So I'm going to have an intersection point at x equals 0 and x equals 2, which is not super helpful that they're in the x, so I need to put them into y. So it doesn't matter which one I choose, I'm going to get the same answer because they're points of intersection. So if I want to know that's 2 times 0, or that's y is 0, so I have my intersection point is 0, 0. My other intersection point is 2 times 2, or 4. So my other intersection point is 2, 4. And since we're looking at going for the y-axis, I'm going to need those y variables. The next thing I need to do is put both of these equations in terms of in terms of x. Right now they're in terms of y. So I'm told that y equals 2x, but I don't really want to know about y equals 2x. I need to know that x equals 1/2 y, or y over 2. And same thing for, so this is going to be important, and the same thing for y equals x squared. I need to know that x equals the square root of y. So those are the important equations that I'm going to have. And I'm going to travel in. So my first equation is going to be the square root of y. And then my second equation will be the red line, or y over 2. So my volume is going to be pi times the integral from 0 to 4. The first equation we said was the square root of y squared minus 1/2 y squared, and then dy. So we'll distribute that squared to both pieces. So pi 0 to 4, that's going to be y minus 1/4 y squared dy. And now I'll take the antiderivative. Pi and then 1/2 y squared minus, I'll go up 1 in the exponent, that'll become y cubed, and then I have to multiply 4 times 3 and get 12. So 1/12 y cubed. We'll evaluate it from 0 to 4. So that's pi 1/2 4 squared minus 1/12 4 cubed, and then minus 1/2 0 squared minus 1/12 0 cubed. So we'll simplify that. Let's see, we get 16 over 2 is 8, and then 64 over 12, which I can reduce to 16 over 3. And let's see, that has to be in as 3. So I multiply by 3 and I get 24. So 24 minus 16. Going to get 8/3. So 8/3 pi is my area for this figure.